Hello and welcome back to yet another lecture on the NPTEL course on advanced plasticity of solid continua. So, we have been discussing the FEM implementation of coupled thermo-visco-plasticity, and in the last class we saw how to derive the purely mechanical part of the tangent stiffness matrix or the material tangent information. Now, that is applicable if there is a weak coupling, very weak coupling between temperature and the mechanical fields like the plastic flow and deformation. On the other hand, for very strong coupling where a change in the deformation field affects the temperature field and vice versa quite a lot, then a fully coupled thermo-visco-plasticity is what is called for, and we need to derive the corresponding tangent information for that case, and this particular lecture is about that. Okay, so let us get started with our work. Now, as you can see that for the fully coupled system, the starting point would be, of course, start with this d sigma, the expression for the differential of stress. But now our objective will be to account for the temperature dependence in this, so that we can write it as del sigma by del epsilon. Epsilon is the strain, d epsilon plus the temperature effect, del sigma by del theta d theta, right? Theta is the absolute temperature. Now, if you call this as the purely mechanical part of the algorithmic material tangent, C alg, let us say C epsilon epsilon alg, this, right? And if you call the other part del sigma by del theta as the algorithmic part of the material tangent, but which accounts for this coupling between temperature and deformation, call this as C epsilon theta alg. Okay, so then we need to determine these two quantities, right? So, first let us bother about the the mechanical tangent first, okay, and then the, of course, the thermomechanical coupling tangent. Both we will derive in this lecture. The starting point for this is obviously the same, that is, just express the stress in terms of the total strain and the plastic strain and also the thermal part of the strain, because temperature dependence is an important thing. So, thermal part of the strain is here, it depends only on temperature, right? So, this, remember, is the fourth order elasticity tensor, right? So, now do not actually mistake this C, the elasticity tensor, with these quantities. These are tangent material information, material tangent information, right? Okay, so let us proceed. Now, you see, whenever we take the differential of things like that, for example, this d sigma, it is a way of linearizing the relationship between stress and strain, right? Because you do linearization in the Newton style by taking derivatives, right, about a point which is known, okay, and then studying the small increments about that point, okay. So, this is my d sigma expression. Note that in the last case, instead of writing this d epsilon theta, we are writing it as d epsilon thermal, d epsilon thermal as delta epsilon thermal by del theta into d theta, okay, because epsilon thermal part depends only on temperature. Now, recall the plastic strain increment given the plastic flow direction Np and the magnitude of the increment of the plastic strain delta lambda, and given the plastic strain at the last time Tn, our objective is to determine it at Tn plus 1. So, it is given this way: epsilon p at any forward time including Tn plus 1 is the last available epsilon p at Tn plus delta lambda times Np. Delta lambda is a scalar, okay, Np is a tensor, a second order tensor, okay, it is a deviatoric second order tensor. For metals it is deviatoric. Okay, so for other cases it need not be deviatoric in all the cases. Yeah. Okay, so now you can actually see from here this expression that if I take the differential of this, again by actually we are dealing with linearization, right. So we have to take differentials everywhere. So d epsilon p is given by, because this part is known, so there is no d applied there, that is fixed. So only this part will be useful in writing the expression for d epsilon p, which is given by np times d of delta lambda plus delta lambda times dnp. Okay. Now recall from our last lecture that in the von Mises plasticity the flow direction, the plastic flow direction is fixed. So therefore dnp is 0 because it cannot change, it is a strictly radial return for the stresses. So therefore in the correction I mean, so therefore dnp is 0. Okay, so we will stick to it. Now let us then proceed further with this simplification. We are linearizing the fully coupled system. So then d epsilon p, neglecting the dnp part, is np times d of delta lambda. Okay. Now you know this part can be put in the stress differential, right. The stress differential d sigma had a part which is d epsilon p, you recall. So now of course it was pre-multiplied by the elasticity tensor C. So that now takes this form by putting d epsilon p from here, substituting it from here, we get this, and of course we have the thermal part sitting as before. Okay. So let us call, like we did in the last lecture, this second order tensor, because this is a fourth order tensor, this is a second order tensor, there is a contraction of a fourth order tensor with a second order tensor. So it becomes a second order tensor, right. So call that second order tensor as u. Okay. We have used the same notation for the second order tensor in the last lecture as well. Now recall that the Perzhino flow rule in the discrete form over delta t can be written as delta lambda equals delta t when the plastic flow is active, that is f is strictly greater than 0. So therefore the Macaulay bracket is replaced by just f itself. So f by mu theta, recall that mu theta is the viscosity coefficient which is temperature dependent, to the power m, where m is, if you recall, the rate exponent, rate sensitivity exponent, right. So basically we have this relationship which we need now to differentiate. Okay, we need to actually take the differential of this because we have this term, right. So we just take a d here, and so we can write this d of when the plastic flow is active, that is we have, by taking the differential of delta lambda, this expression g is a scalar which is given here. Okay. We have used the same scalar in the last lecture also, if you recall, and then we have these two terms in delta lambda, which is basically, you know, one term depends on d sigma. Okay. So you have to take the d of this, right. Remember that f depends on sigma and theta also, right. Similarly mu also depends on theta but not on sigma. So therefore the whole quantity depends on sigma and theta. So therefore when you take the differential there will be two terms, right. One is based on del f by del sigma, which will be of course np. Of course there are other factors which will come, if you just differentiate you will know, and the other will depend on del f by del theta. Okay. So call these terms, write this in terms of this d sigma and d theta, as I am telling you, I have just told you. Okay, the coefficients turn out to be just these two, right, e theta, where e theta is given by this. Remember that e theta is two part, one is del f by del theta from the last expression for delta lambda, and the other mu theta is also a function of theta. So you need to actually apply the appropriate rules of differentiation to get this, right. So, this is the expression for d delta lambda which we must make use of. This is basically the cap z, cap xi or cap z. Okay. Now, substituting this thing into the expression for d sigma, because you remember that d sigma had this d delta lambda. Okay. So, we have now an expression for d delta lambda in terms of d sigma and d theta. So, let us substitute to get this expression for d sigma. Okay. So, you see that d sigma appears on the right hand side also. So, we need to take it on the left hand side, and arranging this way we write the same expression in this manner. Okay. So, this coefficient matrix here of d sigma has to be inverted if you want to write an expression for d sigma. Okay. So, we need to write an expression for d sigma to be sure. The right hand side contains terms connected to d epsilon and d theta. Okay. So, now again, as we discussed in the last class, in the last lecture, all these corrections which are engineered by these material tangents, correction to the stresses, etc., and hence correction to the finding out delta lambda and hence epsilon p, all this happens radially along NP. So, this is a rank 1 correction over elasticity. That is a very important point to remember. Okay, that is true if theta is fixed, otherwise this is not rank 1 correction. So, what actually we are doing here, because we are only bothered right now only on the C epsilon epsilon, you remember that we are now finding only this part of the this part. Okay, this part of the material tangent information. So, therefore, in this we can hold theta fixed for the time being as if theta is fixed. So, basically what we are doing is to assure that in finding C epsilon epsilon, the material purely mechanical material tangent, we can apply this rank 1 inversion for the coefficient matrix of d sigma. We can do it in exactly the same way, the SMW rule, that is the Sherman Morrison Woodbury formula, to write the inverse of this. So, remember that basically U is a second order tensor, NP is a second order tensor. So, their tensor product of two second order tensor gives you a fourth order tensor. This I therefore is a fourth order tensor, right. So, you actually when you take the inverse you write it also in terms of the fourth order tensor in this way. Okay. So, this term here below, you observe that it is basically a scalar, because G is a scalar, NP inner product with U is a scalar, because both NP and U are second order tensors. Okay. So, this is the situation, this is the simple rank 1 inverse, right. So, applying this inverse we can get the expression for d sigma. I am sorry, there is a d missing here, let us put it here. D sigma is basically this part plus this part. Okay. So, this is based on the rank 1 inversion, assuming that the change in sigma is strictly along NP. So, now because if you put all these expressions for the inverse in the expression for d sigma, okay, in the last case from here. Okay. So, put this d sigma equal to this inverse times all this and collect the coefficient part of d epsilon to get our quantity of interest C epsilon epsilon algorithmic. Okay. So, that turns out to be equal to this elasticity tensor minus this fourth order tensor correction. Okay. So, basically this is the correction to the elasticity tensor that we get in the form of this C epsilon epsilon, right. It starts with the elasticity tensor and then there is a correction here. Okay. So, this is the situation for the first part, the mechanical part, but we have to be going further beyond this, because we are dealing with strong coupling with thermal effect. So, therefore, the algorithmic tangent, material tangent for epsilon theta coupling is also important. That is what we actually concentrate on right now. Okay, so, thermo-mechanical tangent. So, that also you can extract from the same expression. So, you just extract the information from the d theta part from here, okay, and that turns out to be this. All right. Now, the thing is that when you do this, of course, you assume, irrespective of whether theta is changing or not, you assume that dNp is strictly 0, Np does not change direction, plus all corrections are radially along Np. Okay. So, then this is the expression that is valid for the coupling part of the material tangent. Okay. Well, so therefore, we can actually expand this, just there are two terms here. So, I have written these two terms explicitly, that is all. Okay. So, therefore, the final block structure for the update d sigma, think of d sigma not just as a differential, but delta sigma. Similarly, d epsilon and d theta as delta theta, delta epsilon and delta theta, some finite change increment. So, that is given by both these material tangents appearing. Okay. So, this together gives me the entire information on the material tangent, right. From this expression for the material tangent, we can write the tangent stiffness also. Now, let us now bother about the full FEM implementation. That means, using these material tangents, our objective will be to go towards developing the tangent stiffness for every element, right. So, because we have been using that, no, you recall that the material tangent is a precursor to the development of the tangent stiffness. Okay. So, now let us do that. In order to do that, you know that there is a thermal source term in the governing equation for heat flow, right, that is that equation for theta. Okay. So, that thermal source term, mechanical source term, is given by Q equals beta times sigma inner product epsilon p dot. Beta is the Taylor-Quinney coefficient, you recall this. If this is the correct form of Q, because beta reduces sigma inner product epsilon p dot, so as to account for the other effect. So, you recall our discussion on the Taylor-Quinney coefficient, which is close to 1, but not exactly 1. So, it is slightly less than the plastic work sigma epsilon p dot, right. So, that is my mechanical source term. We need, for finding the full stiffness, tangent stiffness, we need information on the derivative of this mechanical source with respect to not just strain, but also with respect to theta, both. Okay. So, if you now just recall the expression for Q from here, now take the derivative of Q, partial derivative with respect to epsilon, the strain, then you see that we basically get from, there are two terms, one is sigma, which depends on epsilon, and epsilon p dot also depends on epsilon, right. So, therefore, we can actually see that del sigma by del epsilon by chain rule becomes this purely mechanical material tangent, which is inner producted with epsilon p dot, and the other term by the chain rule has this del epsilon p dot by del epsilon coming in, okay, inner producted with the stress sigma. Similarly, del q by del theta can be found, So, basically del q by del theta becomes this del sigma by del theta, which is basically from our original expression for d sigma, you recall, okay. C, the coupled material tangent, inner product with epsilon p dot plus sigma inner product with delta epsilon p dot by del theta, again by chain rule. So, this gives the, if we get these two terms, then we get all the different blocks of my K matrix. This K matrix will have 4 blocks. This K will be having 4 blocks. So, one purely mechanical, U is the deformation or strain. The other will be U theta, then theta U, these are the off diagonal blocks, and there will be K theta theta, purely thermal block. Okay. Each one of these blocks are essentially matrices. Okay. So, we need to find out all these K, these different blocks of K. Okay. Let us see how to do that. These 2 material tangent information that we have already derived are enough to find them. Let us see how to do that. So, first we have to start with the governing equations, all right. There are 2 governing equations of interest here. One is basically the mechanical equilibrium, which is here, and the other is the generalized heat equation, which is the PDE, partial differential equation, in the temperature theta. Okay. In this we have ignored the piezocaloric term. Typically I have been telling you during the discussion, when we had a discussion on this generalized heat equation, I told you that the piezocaloric effect is often neglected. Okay. So, for the weak form, therefore, because the deformation is one thing and the temperature is another variable. So, del u and del theta be the virtual variations of the test function. Okay. So, these are virtual variations, these are also called test functions. Okay. So, now so what we are doing, remember that we are now actually trying to linearize this by writing the linearize these equations by writing them in the virtual or weak form, in the virtual work like form, right. So, for the mechanical weak form we have this. Okay. So, you understand. So, the delta epsilon comes in because of the variation delta u. These are all virtual variations. These delta, these all are virtual variations. This is the Neumann boundary condition term, and this script T bar, small t bar, is the applied traction on the Neumann part of the boundary of the body. Okay. So, then thermal weak form similarly will be in terms of delta theta, virtual variation of temperature, and again recall that this is basically a linearized form, right, through the derived from the original equation. So, this is the situation. Okay. Now, you see that let us do the time discretization, because there is a theta dot term. We typically deal with theta at n plus 1, theta, not theta dot. So, write theta dot in this finite difference form. Similarly, epsilon p dot you can write in this finite difference form. Okay. So, now in the discrete setup also, this the mechanical heat source term can be written in terms of this delta epsilon p by delta t. Instead of epsilon p dot, we just use this delta epsilon p by delta t. Okay. Now, let us do the finite element discretization of these twin fields, displacement and temperature. So, the displacement is written as the shape functions related to the displacement nu times the nodal displacement variables capital U, and temperature is written this way, n theta times nodal theta, cap theta, let us call it. Okay. So, nodal temperatures, and from there we can actually get the strain displacement relation. For the theta, we need basically the derivative of theta versus theta relation, right, nodal theta information. So, basically these are called epsilon equal to b times capital U, and for theta, grad theta equals b theta, strain displacement matrices. Okay. So, this is not exactly strain displacement, but grad theta versus theta matrix. Okay. So, this is the situation. Now, given these two matrices b and b theta, we need to see, and also the original forms of expansions for finite element approximations for the fields u and theta. we can write our residuals based on the weak forms that we have already formed for the two equations. For the purely mechanical equation, the residual is, you have seen it earlier also, right? That is the integral over omega strain displacement matrix times sigma d omega minus external forces, right? If you have forgotten this part, which we discussed earlier, please go back to the previous, the appropriate lecture number that I do not exactly remember, but you will be knowing. So, if you flip back a few lectures when we discussed this, how to derive this Ru. For the R theta, you can see that this R theta, so both are basically supposed to be equal to 0 ideally if you get the correct solution. Okay. So, R theta corresponds to the virtual form of the the differential equation for theta, okay, appropriately discretized in time. So, this is one term Cv theta dot term, right, and what you have actually done here, n theta is coming from the expression that delta theta is equal to n theta delta of the nodal theta, correct, right, nodal theta, right. So, delta cap theta, okay. So, is this n theta transpose is that n theta, and instead of this delta theta, delta nodal theta comes out, and the coefficient of delta nodal theta is set to 0, and that gives you R theta. You should recall all this, which is very similar to the way we derived Ru. The next term in the expression for R theta comes from the diffusion term, right. So, that gives you B theta transpose, the thermal conductivity K, B theta, okay, n theta Q, n theta transpose, this is the source term in the governing equation, right. And now, if you now recall our last, some days ago we have actually discussed this, that we need to now use a Newton-Raphson method, right, Newton linearization. So, we need to arrive at this equation for the update delta u and delta theta at the nodal level, at the nodal variables for displacement and temperature. These are Ru and R theta which goes into the right hand side. So, you start from some u and theta, that is to say for which Ru and R theta are not equal to 0, and correct it, okay, based on this delta u delta theta. You understand, this is the thing. So, we need all this k u k u theta k theta u and k theta theta for this purpose, right. So, now what we have to do, we need to actually start deriving these quantities, that is not possible to cover in this particular lecture because it will take some time for us. So, what we will do now, we will shift it to the next lecture. So far what we have covered in this lecture is to come to the final stage of the Newton linearization of the residuals, right. Why am I talking of Newton linearization of the residual? Because you see the residuals are purely in terms of theta and u, right. So, you are actually taking a further variation on these residuals, that means differentiating these residuals with respect to u and theta in order to get this information on k, correct, this information on k. So, this derivation of these 4 different blocks of the stiffness matrix k we will consider in the next lecture, and we will see that once these blocks are created, we have a completely coupled, strongly coupled solution for thermo-visco-plasticity, which is eminently implementable through the finite element analysis in a computer. Thank you for your attention to this lecture, and we will meet soon. Thank you.